In this lesson, we're going to look at subtracting vectors. Now, subtracting vectors follows adding vectors nicely because really when we're subtracting one vector from another, we do that by adding the opposite. So we're going to change the direction of one of the vectors, in other words. So what that means is if we were going to add, let's call this one vector u and vector v, I'm sorry, if we were going to subtract them, then we would do that by switching the direction of vector v. So this would be what we would call negative v, since it's running in the opposite direction. And then we would find the resultant vector by adding those two together, which would be right here. So this one would be vector u minus v. Okay, so in this next example, it says express one vector as a sum/difference of the other two. So what we'll do is we'll express it both ways, as the sum, one as the sum of the other two and another as the difference of the other two. So for example, looking at this picture, we can see that if we add vectors r and p together, we arrive at the resultant vector q. And we could rearrange that same equation and say that vector q minus vector p gives us vector r. So in other words, vector q is here. Then if we're going to subtract vector p, that means we would be switching the direction of vector p. So the red one would be negative p. And then your resultant vector would be here, the one that's labeled with an r. I should go over that in a different color maybe. Okay, right there. So we could also say vector q minus vector p gives us vector r. Now in the next example it says, given the following diagram, which is actually out of your workbook, determine a single vector that is equivalent to each expression. Now the only thing is that these should be labeled, and they're not on your handout, so we need to fill them in. So this parallelogram is labeled A, B, C, D, and E in the middle. Okay, so we need a single vector that is equivalent to subtracting vector AE from vector AB. So vector AB is right here, and vector AE is right here. So we want to subtract vector AE from AB. Now, we've said that we're going to subtract vectors by adding the opposite. So this would be the same as vector AB plus the opposite vector, which would be EA. So just changing the direction. So instead of AE, we have EA. So now we're adding AB and EA together. Now, what we can do is rearrange this order and say this is the same as vector EA plus AB, because if we do it that way, we can see that our resultant vector would be this one down here, vector EB. Now, another trick when you're looking at the labels of the vectors, if we have vector EA and we're adding to that vector AB, the resultant then will be the first letter from your first vector, so E, and the second letter from your second vector, which is a B. So this would be vector EB anyways. Okay. Next one, let's label your parallelogram again. So A, B, C, D, and E. And now we're going to find an equivalent vector for CD minus BD. So once again, let's start off by changing this to an addition. So we're going to add vector CD and vector D, B, which is the opposite of BD. Now again, as I was just saying to you, when you are adding vectors, if these middle two letters match, okay, then when you add these vectors together, the resultant will be the two outside letters, so C, B. Now let's look at the picture and see if that makes sense. So vector CD is here, and if I want to add to that vector DB, that would be here. And so your resultant vector is CB right here. So that works. Okay, and the next one, label it again. Okay, so CB minus CA could be written as, sorry, that should be CB again, CB plus AC. So change the direction of the second one and add. Let me see if I can't write that a little clearer. So we're adding the opposite, and the opposite of CA would be AC. So once again, I'm noticing in my labeling that I have C, vertex C, in both vectors. So if I reorder that addition statement and instead write AC plus CB, then we can use this trick I've showed you to sort of cancel out those middle C's and simplify this down to vector AB. But again, let's look at the picture. So we were adding CB and AC. Oh, sorry. In my second line, I was adding AC. Maybe something was wrong there. And CB. So our resultant vector then goes from A to B. Okay, we'll label the parallelogram in the last one. All right, so AB subtract DB. We're going to rewrite that as AB plus BD, so adding the opposite. And that can be simplified down to vector AD. And in our picture, we can see that AB plus BD has the resultant vector AD. So where we started to where we left off. Okay, your next example says, given the regular hexagon UVWXYZ with center 0, or O I guess it is, let OU be vector U, OV be vector V, and OW be vector W. This is also a question out of your book, your workbook. And once again, the labels are not written here, so we will add them in. So I believe the labels start at the top here. So U, V, W, X, Y, Z, and you have O in the center. Now we have vector U, which is really OU. So here's vector U. And we have vector V, which is OV. And our task is to write UV in terms of those two vectors. So UV can be written as the sum of vector UO and OV. So in your picture, that would be going from U to O and O to V. That would have the same result as going from U to V, is what we're saying. Now, if I want to add those together, well, actually, I don't want to add those together. I want to express those in terms of vectors U and V. So it's UO then would be negative vector U, because it says vector u is OU, plus OV, which is vector v. So I could rewrite that as v minus u. Okay, next one, u, v, w, x, y, z, o. Now it says write OW in terms of u and v. So OW is here. Now OW is the same vector as UV. It's positioned differently in space, but it has the same magnitude and the same direction. So those are equal vectors. So OU is equal to UV. And again, that's because it has the same magnitude and the same direction. So now UV is the one that we just did. So these are equal. This would also be V minus U. The next one asks us to write WO in terms of U and V. Now again, on your picture, WO is this vector here. So WO is the same as negative OW, which is the one that we were just looking at in part B. So that would be negative V minus U from part B, which can be rearranged or can be rewritten without the brackets as negative V plus U or U minus V. So you can see there's a lot of algebra involved in these kinds of questions. And the last one is to express xy, which in your picture is down here, in terms of u and v. So vector xy is, again, equivalent to vector wo because it has the same magnitude and the same direction as wo. So these two will be equal. From part C, we know that vector wo can be written as vector u minus vector v. And that completes this lesson.